Namaste, good morning, good afternoon, good evening to all. As per the location where you are at present, I am Nivedita Pathak, coordinator and MC of the session. I feel honored and delighted to welcome you all to the fourth edition of TSTSI Technical Deep Dive session on evolution of broadcast and non-terrestrial networks. Before we begin, I would like to announce a few hygiene instructions. Let me present my screen. If you have any questions for the speaker, please type them in the Q&A tab. If any of the questions from the audience are left unanswered due to lack of time, we will send the same to the speakers via email and respond back to you. You may interact with the fellow attendees live using the chat tab during the session. If you want to enlarge your presentation, please click the expanding arrow icon on the top right of this screen as shown below. The tool is configured for HD. The attendees may switch to a lower mode in case you have any bandwidth issues. It is now my pleasure to introduce you to my co-chairs, Anindya Saha and Anuradha Agrawal. Anindya Saha is the Chief Technology Officer at Shankya Labs with approximately 24 years of experience. He is an expert on software defined radios and has led the design and development of the baseband and RF subsystem for Shankya products in wireless communications. Anuradha Agrawal, she is the member of Indian Broadcast Engineers Service and is currently Additional Director General in Prasar Bharati Secretariat, New Delhi. She is responsible for overall management of a wide range of activities for the Prasar Bharati network, encompassing studios, earth station, and transmitter for Air Doordarshan, which includes policy formulation, planning, induction of new technologies, project implementation, monitoring, coordination, etc. She has over 3 decades of experience in the broadcasting sector. Over to you, Anuradha, ma'am.
Thank you, Nivedita, for giving me this opportunity. Wishing everyone a very warm welcome and a very good day to all who have joined us today from different parts of the globe in session 10 of the TSDSI Deep Dive 2021 conference, the fourth edition of the conference. This session will focus on evolution of broadcast and non-terrestrial networks, and this session is sponsored by Advanced Television Systems Committee, Atsc. It's indeed wonderful to have you all here for this session. The explosion in consumption of content and the change in viewing pattern of the consumer from fixed time to on demand is creating the need to revolutionize the entire delivery system. This session addresses the two important disruptions that will enable this revolution: the broadcast broadband convergence, which is a necessity to enable cost effective service delivery to the mobile devices. The broadcast services also are diversifying to offer services like public protection, emergency, and disaster management, emphasizing the need to accelerate this convergence. The unification of non terrestrial and terrestrial networks is the second disruption. The NTNs are required to complement the terrestrial networks in providing services to uncovered or underserved geographical areas. The NTNs promise improvement in wide area coverage, scalability, service continuity, and its availability. In this session, global deployment case studies and the roadmap for deployments in India will also be deliberated. Today, we have a star studded lineup of prolific speakers from the broadcast and satellite industries to highlight the technological innovations that are enabling these disruptions. We acknowledge them for agreeing to spare their valuable time for this session. I now welcome Mr. Sashi Shekhar Vempati, CEO Prasar Bharati, for delivering the inaugural talk for this session. Mr. Shashi Shekhar Vempati, a technocrat, is an alumnus of IIT Bombay. After his long stint at the Indian Information Technology major Infosys Technologies, He managed a digital news media startup, Neeti Digital, before taking up his current role in public broadcasting, where he is currently overseeing the transformation of the twin networks Doordarshan and All India Radio. He is also an innovator, an author, and a columnist. He also serves on the boards of various organizations, including the Indian Broadcasting Foundation, the BARC, apart from Indian Council of World Affairs and the Public Service Broadcasting Trust. Over to you, sir, for your inaugural talk on evolution of broadcast.
To join the fourth edition of the TSDSI Tech Deep Dive Online Conference 2021. I understand this year the focus of the conference is on standards for digital transformation in the new normal. Very happy to join the breakout session on broadcasting, specifically focused on the evolution of broadcast and non-terrestrial networks. We at India have had a very unique experience with respect to broadcasting. As many of you would know that for several decades after independence, in fact, a few decades prior to independence as well, broadcasting had started in India, and it was primarily the public broadcaster which was the only provider of broadcast services. It started in the 1930s, 1940s with All India Radio. And then in the 1950s, television broadcasting came along with Doordarshan. And then subsequently, in the 1970s, both these organizations grew into separate broadcast arms of the government. And until perhaps the late 1990s, you only had the public broadcaster as the sole broadcaster in India. And then, of course, with the opening up of the Indian economy in the 1990s, you had a whole range of private broadcasters entering the Indian market. And all of a sudden, the Indian consumer who grew up watching Doordarshan or listening to All India Radio was presented with a number of choices. And the whole broadcasting scenario in India changed. It would be interesting to notice a few nuances about this evolution. If you'll recall, historically, on the radio side, we've had medium wave and short wave predominantly for several decades. And then came the FM revolution. It started with the public broadcaster initially in a few cities. And then subsequently, you had private broadcasters also entering the FM market. But the long-range terrestrial broadcasting on the radio side, primarily medium wave and short wave, continued to be the exclusive domain of the public broadcaster. Similarly, on the television side, we all grew up with rooftop antennas, terrestrial broadcasting for several years. And then something changed dramatically in the Indian scenario. Unlike several other Western economies or several other countries, which had an evolution from analog terrestrial television to digital terrestrial television and so on. In India, we kind of skipped a step in between. We went directly from analog terrestrial TV to cable and satellite. And that was a dramatic change. So you had households which had access to a mere single channel to watch on, or perhaps two channels. Now suddenly we're spoiled for choice. And today, India has close to 900 television channels. So you're seeing a dramatic shift from the rooftop antenna terrestrial broadcasting scenario to scenario where set-top boxes, be it cable or DTH, offer a multitude of choices to the consumers. All this was happening, late 90s, early 2000s. And then, of course, with the advent of the internet, the scenario has changed, and smartphones, the scenario has changed even more dramatically in India. We've had an explosion of internet traffic, especially video traffic, with smartphones and mobile phones, with an immense amount of viewing and media consumption happening on these devices over the internet through, be it live events or be it over-the-top OTT platforms, on-demand video consumption. India has sort of redefined the killer app for the internet, so to speak. I recall during the early days of the internet, a lot of debate and e-commerce, a lot of the debate would be focused on, what is the killer application? And at one point in time it was email, at one point in time it was the web browser and e-commerce sites and so on. But with smartphones and low data costs in India, mobile data costs, you have an entirely new scenario where the killer application is video and video consumption. And it's not just live streaming. There's a whole lot of user-generated content and person-to-person video as well, which is driving this revolution in India. So in this scenario, what does the evolution of broadcast really mean? I think this is something that requires out-of-the-box thinking, a very different approach and thought process to the future of broadcasting in this scenario. And I think that is where I see the evolution of broadcast standards being very, very crucial and important. Our consumer today is not sitting in front of a television. Our consumer is not listening to a physical radio set anymore. In all likelihood, our consumer is either listening to FM radio on their earphones on a mobile phone, or our consumer is watching live TV through some kind of an OTT player, be it YouTube, be it Hotstar, or be it any of the apps out there. In fact, I was told that the recent match between India and Pakistan during the ICC T20 World Cup had an online viewership of almost more than 10 million viewers, which is phenomenal amount of broadcast-like video traffic being delivered over the top to mobile phones on the internet. And I think that is the viewing scenario that the evolution of broadcasting needs to capture. Those are the kinds of use cases that broadcasting needs to think about if we have to make it relevant in this end user behavior, changing habits and viewing patterns. So if we have to capture this, we have to rethink the role of broadcasting, the nature of broadcasting. And to me, the answer is very clear that in the future, broadcasting has to be direct to mobile. There was a time when being direct to home was important. That was a decade back. I think decade from now, if we are not direct to mobile, we probably are not relevant as broadcasters anymore. And I think that would be the challenge in front of every broadcasting organization, and more specifically, the public broadcaster. Because the public broadcaster has a very unique role and a very unique responsibility. If you take any democratic scenario, any nation, the public broadcaster has the mandate to not only put out information, news, and live events and alerts of public importance, national importance, but also has a very unique role to play when there is disasters, when there are emergency situations. And all of these require public content of public importance to be able to reach the citizenry across platforms, across devices. So that calls for a whole new range of broadcast capabilities that have to be mandatorily provisioned on end user devices. Now in the world of cable and DTH, we had a law for this, and it is called the Mandatory Carriage Law as part of the Cable Act, which required that the TV channels of the public broadcaster are mandatorily carried on all set-top boxes. Now that was in the world of fixed television viewing. But when it comes to mobile viewing and increasing consumption of video through mobile devices, we need an equivalent public mandate, which requires that the content of the public broadcaster is mandatorily available on broadcast frequencies, which are delivered directly to mobile phones, smartphones, anywhere in India, across networks, across providers. So that I think lays the foundation for what kind of a direct to mobile standard that we would like to see evolve in India, where emergency alerting, disaster management, public content of national interest, public interest finds its way directly to mobile phones in a direct to mobile architecture. And that leads us to the next question, that how should the standards evolve to accommodate this future scenario? How should the standards make way for this future that we are envisioning? One of the architectures that we have already put in place in 19 cities is the conventional way of looking at direct to television, DTT, where digital terrestrial television towers are delivering signals in the more conventional way to fixed television sets. So that is the first place where we would look to enhance that architecture to also be able to service mobile phones, so that we are able to send out broadcast content not just to fixed television sets, but also to people on the go on their smartphones, on their mobile phones. And also from an end user experience standpoint, we would like to see the technology evolve where these capabilities are inbuilt to the mobile phones, just as today you have FM receiver capability built into a smartphone, where you don't need an extra piece of hardware, you don't need a dongle, you don't need a add-on antenna and so on. So something along similar lines we would like to see for direct-to-mobile broadcasting, where this becomes a capability which is inherent in the mobile devices. It is an intrinsic capability, and you're able to build various multitude of applications around this capability. And that is when the true potential of direct-to-mobile broadcasting will be realized. So it is interesting for me to see the efforts in different countries. For example, with Atsc 3.0 in Korea and the United States, with LTE broadcast, some of the work that's being done in the European Union. Also some of the efforts around 5G broadcasting, which have part of the 3GPP standards. Perhaps what is required is to bring in an India-specific dimension to these standards efforts, because what work is going on in the other countries does not factor the unique needs of the Indian market, the unique demands of the Indian scenario. And so I'm very glad to see that there's a lot of innovation that's happening in India, a lot of research that's happening, thanks to the leadership that TSDSI has taken, and the collaboration that TSDSI has established with Atsc in the United States, roping in very premier, eminent institutions in India like IIT Kanpur, startup companies like Sankhya Labs and so on. So there's a need for a direct-to-mobile ecosystem to evolve in India, and I foresee TSDSI playing a very crucial role as a catalyst in making this happen, and the intellectual capital coming out of our premier institutes like IIT Kanpur, IIT Bombay, IIT Madras, being very important in ensuring that India emerges as the intellectual fountainhead for the innovation that will happen in the area of direct-to-mobile broadcasting, and especially with a lot of interest around 5G and what the promise of 5G is going to be in the years to come. I see that 5G broadcasting to be a very low-hanging fruit, and given the efforts that are happening in large markets like the United States, given the similarities between India and the United States, perhaps this collaboration that TSDSI and Atsc have initiated last year can ensure that these low-hanging fruits can be realized between these two large economies and two of the largest markets for mobile data, mobile broadcast services in the world. So I very keenly look forward to those efforts, and it is also important for us in India, especially as India's public broadcaster, to see this future happen, and we are committed to seeing this through, and we've collaborated with IIT Kanpur in this direction, and we hope to see that a roadmap emerges for the evolution of terrestrial broadcasting with a direct-to-mobile future in mind. This direct-to-mobile future will also have radio and audio streaming as a very important component. We in India have a very expansive radio network which services very diverse needs. Today we have made some efforts in bringing this entire diversity of radio content, live radio content onto a mobile phone through an app delivered through traditional content delivery networks. And so this is something that we would also like to see happen over the broadcast infrastructure through direct-to-mobile broadcasting and with hybrid use cases where audience measurement can also be built in. So we can make radio measurable. We foresee a multitude of such use cases, and that's what makes the direct-to-mobile broadcasting vision so essential for the public broadcaster, and a very unique India-specific requirement is what we would like to see happen in the standards. So my call to action today at this forum would be for TSDSI to lead these efforts, bring in all the stakeholders, and to ensure that we have a D2M roadmap that emerges with everyone's buy-in, and it becomes a global standard in line with whatever is in store for the future, be it 5G, 6G, and so on. So once again, my very best wishes to TSDSI for this conference, online conference, and my very best wishes to all the participants, and hoping to very soon in the near future have a live demonstration of direct-to-mobile broadcasting with the state-of-the-art mobile phones and a very compelling user experience. So thank you again for having me for this keynote today.
Thank you, sir. Thank you, Shashi sir, for your engaging deliberations on the evolution of broadcasting in India from the rooftop terrestrial TV to a cable and satellite systems and on to the internet through the apps, from a single channel to multi-channel, and then from the fixed devices to now mobile devices, wherein we, from our experience, Prasar Bharati is already available through the News on Air app, at least on no number of radio channels. The expansion in the consumption of content over the mobile devices is certainly increasing as on today. And you have correctly pointed out that earlier it was D2H, that is direct to home, which is now converting into direct to mobile. So the roles and responsibility of the public broadcaster, as you have rightly said, are immense. And Prasar Bharati, as a public broadcaster, would certainly, surely under your able guidance, be moving towards the direct-to-mobile infrastructure development and deployment. Standards certainly need to be made to address these issues, which you have certainly pointed out, and addressing these issues for delivering the content not only to fixed devices but to mobile devices and on the go will certainly make way in the near future with, and the ecosystem development for the direct to mobile is also equally important, which you have very very effectively made your point. And certainly I would like to see that the device ecosystem also develops simultaneously with the deployment of the infrastructure. Thank you so much, sir, for your interesting deliberations. The next speaker in the forum is Madeline Nordland. She is the president of Atsc, Advanced Television Systems Committee. She is widely respected for her consistent building leadership style. She has chaired the Atc Technology Group that oversees the Atc 3.0 Next Generation Broadcast Standard before being named Atc President in 2019. She previously chaired various Atc 3.0 related specialist groups, ad hoc groups, and implementation teams since 2012. She is a 15-year industry veteran, and she held key technology management and standards roles at Backchannel Media in Telvu Group, the LG Electronics. She also received the TV News Checks 2019 Futurist Women in Technology Award, and she was named one of the 2018's most powerful women in consumer technology by Dealerscope magazine. In 2016, she received the ATSC highest technical honor, the Bernard J. Hencher Outstanding Contributor Award. She is a graduate from the University of Massachusetts. Over to you, Madeline, for your presentation, please.
Hello, my name is Madeline Nordland, and I'm very happy to be here to present to you a heterogeneous network approach to optimize spectrum efficiency. My name is Madeline Nordland. I'm the president of the Advanced Television Systems Committee. This organization is a standards development organization founded in 1983, focused on digital terrestrial broadcasting. There are approximately 150 member organizations in Atsk, and we produce voluntary standards for the broadcasting industry. Our members span the entire broadcast ecosystem, from consumer receiver makers to broadcasters to everyone in between. Today, I'd like to talk to you a little bit about the case for a heterogeneous network approach according to spectrum efficiency needs, and a consideration of ATSC 3.0 and 5G convergence, along with an example technical solution architecture, and then about the ATSC activities that are ongoing today to support a heterogeneous network approach. First, I like this picture because it shows how finite and scarce the spectrum resource is. This is the spectrum resource allocation map of the United States. It's kind of an eye chart, and clearly every square inch of spectrum is spoken for. So how can we increase spectrum efficiency? There are certainly some engineering solutions that are already being employed all the time: better data compression, such as advanced video codecs; reduced overhead, which is better header compression. These are all examples. Definitely the radio access networks are now approaching the Shannon limits, especially in DVB-T2 and ATSC 3.0. But there are also usage solutions. So for example, there's something that I consider to be called time sharing, where there are guest users that are able to use the spectrum when an incumbent is not using the spectrum. This goes on, for example, in the coastal areas of the United States, where certain areas of the spectrum are reserved for the Navy and the Coast Guard, but they're not used very often by those incumbents. And so there are mechanisms to allow others to use that spectrum during the periods that the incumbent doesn't need it. Another approach, which is the one I'm going to be talking about, is the heterogeneous network approach, where you dynamically select the most appropriate network for each use case, as documented, for example, in ATSS in the 5G ecosystem. It's interesting, 3GPP envisions convergence. They have information, particularly starting in release 16, that 5G will be an ecosystem that includes many different standards operating on different spectrum bands and providing different services. And 3GPP has defined methods for steering, switching, and splitting data sessions across the heterogeneous networks. This is the ATSS document that I referred to just a minute ago. And ATSC certainly envisions convergence and has since ATSC 3.0 was developed. ATSC 3.0 is 5G ready and could be part of the 5G ecosystem and part of the entire wireless connected world. ATSC 3.0 and 5G share some common components, including IP transport, HTML5 JavaScript, audio video compression, and more. There are also a number of numerology comparisons in the physical layer. ATSC 3.0 can deliver audio, video, and data to mobile and fixed terminals in large geographic areas, specifically one-to-many communications to large numbers of terminals simultaneously, a point-to-many point wide area network. So if we think about the heterogeneous network approach, different networks, infrastructure, and frequency bands excel at different use cases. The ability to dynamically steer, switch, or split data sessions across different data networks allows optimal usage of the spectrum. So large data sessions intended for a large number of devices can most efficiently be carried in a point-to-multipoint network. So for example, software or firmware updates that need to go to many, many devices is one good example, and popular media content, particularly viewed in linear fashion, is another good example. So a key use case for convergence is to intelligently and dynamically choose one-to-one networks versus one-to-many networks according to the need at the time. And ATSC 3.0 is designed for convergence. It's currently the world's most efficient point-to-multipoint wireless data delivery standard, and it's the first IP-based digital terrestrial transmission standard. It's designed for fixed and mobile, TV and non-TV, linear and file-based delivery. So these characteristics together suggest that Atsc 3.0 and 5G convergence can be technically feasible and can increase spectrum efficiency by choosing the best network for the best thing at the right time. So one scenario that we've been discussing is the traffic offload, broadcast traffic offload in particular in India. So mobile video traffic constitutes more than half of all mobile traffic globally, representing 59% of mobile consumption in 2020 and predicted to be 77% by 2026. Meanwhile, about 6.9% of the Indian people have televisions. The translation of that is they are all watching television services on their phones. So there are more than 1 billion smartphones in India, and the number is growing at a rapid pace year over year. Offloading linear video traffic from cellular to broadcast can reduce traffic on the cellular spectrum allocations and optimize the value of the broadcast spectrum allocations. So broadcast traffic offload is an example of a usage solution per the slide that I showed a minute ago, but it still requires technical solutions, of course, from the engineering community. So Atsc 3.0 is a very highly efficient physical layer. It approaches the Shannon limit very, very closely. And it's also excellent for mobile reception. It does a very good job against the Doppler effect. So it's a great tool for sending lots of data to lots of devices at the same time. Very, very efficient. And I'd like now to talk about a particular solution which was proposed by Carlos Barjo et al. It's called Limitations of ATSSS Technology in Atsc 3.0 5G Convergent Systems. This was published in IEEE BMSB 2021, and the paper is a result of an ETRI-funded project between ETRI and UPV. And I would like to gratefully acknowledge ETRI and UPV for their permission to allow me to show some of the information from this paper to you today. So the abstract is there. It's exploring the use of 3GPP technology ATSSS in order to enable IP layer convergence between 5G and Atsc 3.0. The paper explores this and describes the joint use of 5G and Atsc 3.0 access networks using traffic offload as an example scenario. So the paper actually identifies extensions to current standards that would be needed and proposes a solution architecture. And I'm here to introduce to you a few points that they made in the paper. I encourage everybody to download this paper. It's very interesting. And I would say there's plenty of work to do for the engineering community if they're interested in this particular project. So they identified areas of development that would be required in order to move forward with this converged plan. So they proposed a solution that adds capabilities and methods for using the 5G radio access network for all uplink data carriage. In short, the ATSSS standard expects the 5G network, of course, and the other network, whatever that may be, to have both an uplink and a downlink. In the case of Atsc 3.0 and any other broadcast standard, there is no uplink. And so we need to have a solution for providing for the uplink in these kinds of scenarios. So what they did was they talked about how the user equipment must always initiate the session via the 5G RAN. So currently the way ATSSS is set up, the quote unquote untrusted scenario, meaning the scenario where the cellular operator does not have control over both networks. So in other words, the cellular operator and the broadcaster maintain sovereignty over their own networks. That would be called the untrusted scenario in the ATSSS parlance. And in that parlance, they expect the convergence in the ATSSS, they expect the convergence to begin with the user equipment contacting the other network's core. And in the case of a broadcast standard, that cannot happen because there's no uplink. And so they add capability for the user equipment to start the session using the 5G radio access network rather than the other network. Also, the user equipment always has to acquire security keys, and that generally means that there needs to be an uplink. Unless you can find a way to put the security keys into the device at manufacture, You have to have an uplink in order to get the security keys for encrypted content. And in the case of ATSSS, again, the standard expects those keys to be available via an uplink on the other network. So in the case of ATSC 3.0, the paper has proposed a solution whereby you can use the 5G radio access network via the N3 IWF to access the encrypted content and the necessary keys. And lastly, the control plane data must always be carried by the 5G radio access network in this scenario. Only the user plane data is carried by the non-3GPP radio access network. In other words, the video itself in the case of a traffic offload scenario for a television service. The proposed solution also thinks about the synchronization protocol to coordinate non-3GPP and 3GPP RANs. So seamless switching requires synchronization between the radio access networks to avoid a need for very large buffers. In the case of this particular paper, a solution was not presented for this particular limitation, but I have seen seamless switching in a number of demonstrations where traffic is offloaded from a cellular network, in the case of the demonstration I saw from LTE, onto a broadcast network, in that case ATSC 3.0. It was a linear video service and the switch was seamless. So certainly the synchronization protocol has been considered by implementers in the past, but just not in this particular paper. So again, there's lots of interesting work to be done here in the engineering community to solve some of these questions. Here's some details that are from the paper. As you can see, in the left-hand side, you have the introduction of the ATSC 3.0 gateway connecting with the 5G core. And the ATSC 3.0 gateway is something that exists today for ATSC 3.0 broadcast services, but in this architecture, two new functional blocks are added, the 5G application function and the IP security client. So these two new functional blocks, the 5G application function connects to the MNO network, the MNO NEF per 3GPP to request and serve petitions to create, modify, and destroy services. ATSSS, quote, untrusted connections demand IPsec connections between the UEs and the non-3GPP access to the 5G core. So in this case, the IPsec client connects 5G core via N3IWF per 3GPP. And in the proposed architecture, IPsec tunnel is terminated as the data enters the ATSC 3.0 network. In that case, the ATSC 3.0 gateway is represented as the end device to the 5G core in this particular solution. The solution also suggests adding quick server to ATSSS user plane function and quick client to the user equipment. So ATSSS describes two delivery modes, multipath TCP and lower layer. And the quick protocol can provide the framework for access network operations. Access network operations. The baseline for Quick V1 is used on the 5G RAN, and Multicast Quick is used on the ATSC 3.0 radio access network. ATSC 3.0 and 5G each have an IP pairing to allow the Quick client to switch or steer the data session. I should also add that this particular solution does not address splitting the data session. In this case, we're really just concerned about picking the right network in the first place or making the switch on the fly as content becomes more popular and more efficient, therefore, to send over broadcast one-to-many rather than one-to-one, point-to-point. I'd like to talk about a few projects within ATSC that are here to support this effort. First, the ATSC Broadcast Core Network project. It's going on in one of our technical specialists group, and it's being led by Ali Dernaika of Hewlett-Packard Enterprise and Kevin Shelby of Coherent Logics. The project is underway to specify a broadcast core network that's agnostic to the DTT system. And the idea is that it can accommodate scenarios where an uplink is always available, never available, or sometimes available. And the uplink would be another network, such as 5G or LTE. It will also be designed for standalone broadcast-only operation, as well as for converged operation with other data delivery networks. You could envision a broadcast-only operation where an organization wants to get a certain data delivery to a very large area network, for example, an entire country. And then the request for proposals for technologies to be included in the standard will be issued in the coming weeks, and we look for robust participation in this technical process. Second, ATSC is working on an inter-tower communications network. This is the implementation team 5, led by Dr. Yian Wu of the Canadian Research Centre. The project is underway to test and validate an inter-tower communications network, which will enable for both one-way and two-way communications amongst and between broadcast towers. You can envision a single frequency network scenario, high power, high tower, transmitting backhaul data to smaller towers in a single frequency network. And you can also envision a mesh network scenario with two-way communications among any number of towers. And IT5 envisions a full duplex of two-way communications within a single RF band. Line of sight and professional grade transmitters and receivers that are mounted on the towers can optimize the efficiency and thus minimize the bandwidth needed for the inter-tower data transmissions. ATSC has also started a new project called TG3 Ad Hoc Group on ATSC 3.0 5G harmonization. Some of the parts of the paper that I produced, that I showed just recently, this is just one solution architecture that's been proposed and perhaps demonstrated and in some case worked on in the field of many that have been discussed. The goal of TG3-11 is to consider all the various architectures that are possible for an ATSC 3.0 5G converged network. So it's a new TG3 level ad hoc group formed on 30 September to focus on the potential convergence. We have Anders Askarp from Hewlett-Packard Enterprise leading the group, and the expected work items include certainly a deep review of the 3GPP activities and technologies, and to identify and document potential solution architectures for ATSC 3.0 and 5G convergence. These could be layer 1, layer 3, or core network-based solutions. And the group is expected to report its findings to TG3. So ATSC is actually very busy with all sorts of ongoing projects, and this is one of our key goals, is to ensure that ATSC 3.0 can interoperate seamlessly with 5G networks. We think that's an extremely important aspect of the broadcast community, and our hope is that this work will translate to other DTT one-to-many data transmission standards. I'd like to express my deep thanks to TSDSI. TSDSI and ATSC have an MOU together, and which encourages the sharing of information and ideas. And I must say that ATSC is very grateful for the kind expertise and guidance of TSDSI, and we welcome and look forward to our ongoing collaborations. Thank you for your time today. I'm looking forward to the balance of this session, and I am available for Q&A. So thank you very much for your kind attention, and I look forward to the next parts of the session.
"5G convergence with ATSC, driven by the heterogeneous networks, it was really enlightening. Intelligent and dynamic choice of one-to-many and one-to-many will be very interesting for the future of broadcast. ATSC solutions and methodology for ATSC and 5G convergence would certainly guide the future of broadcasting. Thank you for your interesting presentation. Now our next speaker is Dr. Jordi Glenich, and he is the head of technology at the 5G MAC group. His brief introduction I will try to speak out. He is the head of technology at the 5G Media Action Group, the global association bridging the media and ICT industries to develop the standard-based ecosystem for media distribution, production, and contribution using 5G. During his career, he has been involved in standardization activities within TVB, ATSC, and 3GPP in the domain of next-generation media distribution. He is author of several patents, international scientific papers, and book chapters, and received an IBC award in 2016 for his research in wideband broadcasting, together with Terracom and Panasonic. Prior to 5G, he was a researcher in the ITEAM Research Institute of the University at Polytechnic de Valencia, Spain, and the project manager at IRT, Germany. The topic of today's presentation is titled as Shaping 5G for Broadcast, Multicast, and Satellite Access. Over to you, Jordi.
So it's a pleasure to be here on this session on the evolution of broadcast and non-terrestrial networks. My name is Jordi Jimenez. I'm the head of technology of the 5G Media Action Group, 5G MAC. And today I will be talking about the evolution of broadcast, multicast, and satellite access in the 5G ecosystem. I will be doing this from the point of view of media. So 5G MAC is an association bridging the media and ICT industries in order to work on solutions for media production, contribution, distribution, and consumption of content. Basically, we have realized that connectivity is playing an increasing role in media production and contribution. For instance, now you just get a camera and a backpack and you get connected directly into your TV studio or in the cloud. No need for cumbersome equipment anymore. And we see similar situation happening in the domain of media distribution and consumption. So before, perhaps your target or the main target was a TV at home, but nowadays it's not just a TV, it's a smart TV, it's a TV box, it's a smartphone, it's a tablet, it's a connected car, or it's even a wearable smartwatch and smart speaker and so on. So we realized that most of these technologies, most of these IP technologies were not conceived from scratch, let's say, to deliver media. That's really just coming into the market, and it's a reality. And well, we believe it's time to really make sure that these technologies, as they arrive in the market and as they need to, in the end, serve audiences that are consuming services on them, that we make sure that the technologies are designed and appropriately deployed to meet the requirements of the media industry in the domains of production, contribution, distribution, and consumption. So, well, in terms of content distribution, one of our, let's say from our members, one of our main target is to deliver content anywhere, at any time, and to any device. So it makes sense to work on global standards that in the end can get support on global devices because, well, it makes sense, for instance, to deliver services into smartphones working on the ecosystem of these smartphones in terms of manufacturers, in terms of chipset vendors, in terms of network operators, and so on. The same for the upcoming connected cars with 5G connectivity, and the same for any device that will arrive in the market in the near future, for instance, for IoT and so on. So it makes sense to work on global standards. And the needs are, well, diverse, I would say. There is a diversity as well in terms of content, TV, radio, video on demand, immersive, personalization, targeted advertising, and so on and so on and so on. All of this is actually, well, increasingly going online, and we believe there is a role for the media industry to play in this ecosystem. For this, thinking of global standards, well, 3GPP and 5G here are the most evolved standards at the moment in order to reach smartphones, tablets, but as I said, we see an increasing role in connected cars, in home gateways with offers that are currently going into your home and so on. And even more, 3GPP provides, or 5G provides the possibility to, well, not just concentrate, let's say, on mobile broadband, which of course is an important, or the most important track for 5G connectivity, but 3GPP has also been working on technologies to address the needs for terrestrial broadcasting and the possibility to deploy a 5G system for terrestrial broadcasting, and the same for satellite. So there is a lot of work and a lot of standardization effort put at the moment in 3GPP in order to standardize the satellite components of the 5G system. Just going a little bit more into details, let's jump to terrestrial broadcast. So in this aspect, 3GPP has been working on the so-called LTE-based 5G terrestrial broadcast standard, and it's basically a terrestrial broadcast standard as anyone else, but developed by 3GPP and therefore able to be supported in a regular, let's say, 3GPP enabled device, 3GPP chipset, and so on. So no need to add any other system or any other silicon into a regular smartphone. But in the end is what we want, to reach smartphones that anybody in the world can buy. So basically the system is able to offer a wide set of configuration options, numerologies, cyclic prefixes in order to adapt to terrestrial broadcast infrastructure, for instance in SFM mode. It allows the configuration of carriers with 100% broadcast content, so there is no unicast in the downlink carriers, and even more, it doesn't need an uplink to operate. That's a basic functionality, this receive-only mode, so the possibility to deliver free-to-air content to devices that do not have a SIM card, or that, well, they can have a SIM card, but in the end, the SIM card is not used, this service subscription is not used in order to consume content coming from a 5G terrestrial broadcast network. The system is fully IP-based, so it's compliant with the Dash HLS and CMAF framework. And in the end, well, it allows, for instance, all these applications that we have seen, applications for delivering radio, for delivering TV into the smartphones. Well, these applications can easily be adapted in order to receive content from an LTE-based 5G terrestrial broadcast network. Here we have an example. So you basically can deliver linear TV and radio from a dedicated broadcast infrastructure using this standard. The content can be free to air. I mean, there is no difference, let's say, to any other broadcast standard. So you just deliver content into your 5G device. Well, part of the content can come via broadcast, free to air. Part can come via broadband with your regular connection in your smartphone. Therefore, well, opening the door also for hybrid services. So the standardization in release 16 completed a set of features in order to meet the requirements for broadcasting, and in particular public service broadcasting. But the evolution of the system continues. So standardization in release 17 has been started in order to enable that traditional broadcast bandwidths, 6, 7, and 8 MHz, can be used under this system in addition to the regular LTE bandwidths that already exist. And release 18 is expected also to add support for the deployment of the system in the UHF band. So in the end, we will have a 3GPP system, a 3GPP broadcast system that is able to be deployed in both IMT and broadcast spectrum with 6, 7, 8 MHz, so able to be deployed in the UHF band in any of the ITU regions. So this is the work that has been done in 3GPP so far, let's say, on this topic. But from 5G MAC, we also we have participated in the 3GPP workshops to define release 18, and we also, our members, would also like to propose some additional enhancements, like the connection of LTE-based 5G broadcast to a 5G core, as at the moment this is running on an EPC, on an LTE 4G core, as I said. We also propose the optimization of the simultaneous support of LTE-based 5G broadcast and new radio unicast, so that, well, in the end, you can watch TV, listen to radio over one system, and operate broadband with regular unicast, and also additional proposals in terms of, for instance, adding time interleaving to increase the robustness of the system. That's on the terrestrial broadcast field. On mobile broadband, well, the approach from our members here is a little bit different, so it's more focused, obviously, on mobile broadband networks with the possibility, let's say, to target an online distribution future, fully online distribution future, in which, in the end, all the content is delivered over 5G network. So here, our focus is on two topics in 3GPP. One is the 5G media streaming, that in the end is a system that, or it's a layer that can interface content towards unicast, towards multicast, and towards broadcast. So it's an overlaying architecture offered to service providers, to broadcasters, in order to deliver content in the end in the networks that they are currently using to deliver content. So nothing is 100% broadcast and nothing is 100% unicast at the moment. So there is a mixture and a transition on these networks, and well, we believe this offers new opportunities to create new services and to also control the way services are delivered and consumed by the users. And the other topic is 5G multicast broadcast services, which well, is a new topic, let's say, or a new set of specifications that are coming at the moment in 3GPP for new radio. And well, our members are also interested in understanding how this plays a role for media distribution. As I said, 5G media streaming standardization started in release 16. It provides, well, here you can see some boxes. It provides a series of tools that broadcasters and service providers are going to need in the future in order to deliver content over 5G in a way that is not, let's say, best effort, not just well, delivering something on the network and you never know what happens with the content. So the idea here is to provide tools to have a better control and to optimize the way this content is delivered. 5G media streaming has been working on release 17 on adding extensions, on adding functionalities for multicast, and also on integrating cloud and edge computing capabilities into the architecture. Multicast broadcast services, MBS, standardization started in release 17. The system is based on 5G new radio, and it adds support for 5G in terms of multicast. So, for instance, users can be grouped to access a specific content that is concurrently consumed by many users. And they are also able to provide feedback in order to, well, optimize, let's say, the way content is delivered to this group of users. It also adds support for broadcast, so that content can be delivered not only to a group of users, but to an area, to a service area where any user there can consume content. One of the functionalities that it adds is this dynamic switching between unicast and broadcast. So, well, several users start consuming unicast the moment you reach a certain number of users, and where you see that radio resources can be optimized, well, you can transit these users to broadcast. So on these two aspects, on 5G media streaming or media distribution in release 18 and MBS, well, we are also having a look at the evolution in terms of enhancements, in terms of adding universal access or free-to-air access into the, let's say, the broadband scenarios, the use of or the development of hybrid unicast, broadcast, multicast delivery improvements, and how this can play a role for media distribution, and the enhancement of traditional media with well, Ultra HD, HDR, 8K, and so on. In terms of MBS, our members are proposing here, as I said, the possibility to incorporate a mode free-to-air mode into MBS, so that, for instance, from a mobile network, you can deliver content free-to-air, therefore creating new commercial arrangements between service providers and operators. The addition of multicast reception in active states for the phone, the support of single frequency networks, little bit, let's say, beyond the current scenarios, but into coordinating different GNOT-Bs or distributed units. So all of this is all what you have on the screen are the proposals sent by 5G MAC to 3GPP. And finally, on terms of satellite, well, we believe that satellite can also play an important role actually in delivering content to 100% of the territory, right? So satellites are best placed to deliver massive content to large audiences. And well, with the upcoming, or with they are already here, but with all these new constellations, LEO, MEO, and so on, well, we believe that this can play an important role in order to deliver content to vehicles, but also to airplanes and so on. So in that sense, well, we have been tracking the work in around satellite in 3GPP. So well, here basically there are two architectures or two scenarios using satellite just as backhaul, let's say, connectivity between the core network and the terrestrial radio access, or actually using the satellite for access to the end user. And well, I would say both scenarios are relevant to us, relevant to media, as soon as, well, most of the content in the end is going to be most probably video. So well, we are interested on this. I would just comment on because I know there is another presentation more focused on satellite, but I would just comment, well, the series of enhancements or proposals for enhancements that has been submitted to 3GPP recently. And you can see that, well, a bullet point on this list is the support of multicast broadcast services, which in the end is something that 5G MAC is also looking at for terrestrial. But well, we believe that also media streaming or anything that, let's say, is compliant with the 3GPP ecosystem can be integrated together, and therefore make use of satellite for also distributing media. Additional things, so it's not all just about technology and about the standards. So we need to understand, or at least the media industry needs to understand, the ecosystem of 5G, which may be different to the traditional fora in which the media industry have been engaged. So this has nothing to do, I can say, to other, for instance, broadcast SDOs and so on. This is a complete 3GPP is a complete different story, and it's important that the media industry understands the challenges and the opportunities in the end to play into this ecosystem. Would also like to conclude by saying that we are not 5G MAC only, as I said, developing standards or trying to give our voice into standard bodies, but actually implementing technology, implementing the standards, putting the standards into play together with media applications. And well, our members have recently kicked off this open source development program, in which well, it's open to the development community and to the entire industry, not just to 5G MAC members. And well, anybody can come and provide, let's say, development resources in order to develop the 5G standards for media distribution. We have started with distribution, with media streaming and LTE-based 5G broadcast for release 16, and we plan to extend this as soon as new standards come into play, come into 3GPP. So, well, that's a little bit, let's say, the other side. So I think it's important not just to talk about the standards, but also to put them into play and to implement them, detect bugs, provide feedback to the standardization process, and so on. So that's my presentation. Thank you very much.
Giving us insights about 5G MAC, standards for content delivery anywhere, anytime, and to any device is the key for the future. 5G connectivity for mobile devices, besides 5G for terrestrial satellite broadcast, would really be interesting and of great interest to both broadcasters and mobile operators, besides the viewers. Contributions of 5G MAC to 3GPP involving the 5G terrestrial broadcast in Release 18 would be the game changer. Future works in 5G multicast broadcast services would be interesting. Dynamic switching from unicast to broadcast is also going to become an integral to the content delivery networks. And the challenges that you brought about, concerned with the 5G ecosystem development and implementation were equally interesting. Thank you, Jordi, for an interesting presentation. Now I hand over the session to my co-chair, Mr. Anindya, for the question and answer session. The floor is open for QA.
Thank you, Anuradha-ji. Thank you, all the speakers. I think it was a great session going through, all the insights from the experts. Coming to the Q&A, I see one question here, which I think Madeline has already answered partially. I'll repeat the question. If the ATSC3 is already 5G compatible, why isn't it being considered as the de facto standard in India? DVBI and FEMMS seem to be years away. Any of our speakers would like to take that?
This is Madeline. Certainly, I defer to Jordi to speak more about FEMBMS. That was a main piece of his presentation. I think one of the points that I did want to make, though, is that DVBI is kind of not apples to apples with FEMBMS or ATSC 3.0 or DVB-T2. DVBI is kind of an upper layer thing, whereas the other standards, FEMBMS and ATSC 3.0, that the questioner posed, are full system physical layer systems. ATSC 3.0 also has upper layer. So they're a little bit apples and oranges to think about that, but certainly to think about ATSC 3.0, FEMBMS, and other systems is an interesting question. But of course, I'm certainly not in a position to talk about what India might choose as a de facto standard. But one thing I will say is that it's very, very exciting to me to see the public broadcaster and the TSDSI here together in the same session discussing these kinds of questions together. To me, that's one of the most important things, where within India, the specific use cases of both the mobile world and the broadcast world have a forum to discuss the use cases and to understand what the unique needs of India are. And then TSDSI has the infrastructure to start working on any standards development that needs to take place in order to support those words from India, those needs from India. Thank you, sir.
Yeah, thank you, Madeline. Jordi, your comments or your insight on the FEMBMS part? Jordi, I think you're on mute. We are not able to hear you.
Sorry, now yes. I was just saying, okay, now I think so, right? I was just saying that thank you very much for inviting and for setting up this very interesting session. So on the FEMBMS or LTE-based 5G broadcast side and so on, I mean, there's a lot of work that has been done in 3GPP to enable the system. I mean, the system started as a pure cellular system, and from release 14, it has been evolved into, let's say, downlink only, broadcast only terrestrial network system. In terms of device capabilities and device support, well, that's our main target, to get device support. We can develop a lot of systems, but at least in Europe, I mean, there is no DVB, there is no DAB, nothing into a smartphone, and the expectations are not very promising in that respect. So that's why we are jumping directly into the 3GPP ecosystem. to work together with the technology that is let's say that is almost ready on chipsets. If you look, there is a lot of support for MBMS from pre-release 14, and obviously as the standardization cycle finishes, just remember that there is work in release 17 for the bandwidths, there is work in release 18 for the UHF band. Well, these improvements will get adopted into chipsets and into devices. I mean, we want to work with big manufacturers in order to be on all devices, right? It doesn't make sense to send content just to a few number of supported devices. We want to target global markets in order to scale, let's say, with these technologies.
Thank you, Jordi, for that insight. I think ecosystem plays such a vital role in all of this in adoption of technology. So thank you. Thanks to all the speakers. I think I'll move over to the next session. The next speaker, I'm sorry. Can we put up the bio of Mr. Dr. K.S. Parikh, please? Yeah, so I think we are now moving over to the session, to the speakers who are focusing on the non-terrestrial networks. So the next speaker is Dr. K.S. Parikh. Dr. Parikh did his graduation from MS University of Baroda in Electronics and Communication in 1986. He is working with Space Applications Center, ISRO, Ahmedabad. And he has worked on several indigenous design and development of satellite communication, navigation payloads, for INSAT, GSAT satellites, and he's currently the Associate Director, Program Director, and Deputy Director for Satcom and Navigation Payload Area at SAC. So over to Dr. Parikh for his talk now.
Today I'll be talking about the evolution of satellite communications. The satellite communications worldwide started with the launch of first experimental satellite in 1963, which was SYNCOM-1, which was followed by the launch of first commercial communication satellite Intelsat-1 in 1965. In India, ISRO, we also started our journey of satellite communications with the launch of first communication satellite Apple in geostationary orbit in 1981. From there, today we have reached a stage where we have launched our own high throughput communication satellite GSAT-11 in geostationary orbit. This particular satellite operating in Ku band has a capacity or throughput of about 16 gigabits per second. In India, we started the Satcom services with the INSAT series of satellite called Indian National Satellite System. We had INSAT-1 followed by INSAT-2. The INSAT-1 series of satellites were built and launched from foreign soil, whereas with INSAT-2 series, the satellites were designed and developed in India indigenously. However, they were launched from the foreign soil using foreign rockets. The basic Satcom services which were provided by the INSAT series of satellites were satellite communications for long-distance telephony, as well as services using VSAT or very small aperture terminals. Initially, these satellites were also used for developmental activities by the government for telemedicine and teleeducation. The satellites were also used for broadcast services for television broadcasting, followed later on for direct-to-home or DTH services. The satellites were also used for television and radio networking services. They were also used for other services like mobile satellite service MSS for the satellite-based search and rescue operations, and later on for satellite navigation services. The satellites are used for broadcast satellite service or BSS. They are mainly used for television content distribution and for DTH services. Initially, these services were using S-band frequency range, and later on we started using C-band, and thereafter using Ku band. Initially, the power or the EIRP from the satellite was lower, but with time, the power also increased. Initially, the BSS services were used for television rebroadcasting, and thereafter, the era of cable TV content distribution came. And later on, the direct-to-home services were evolved. Today, we have about more than 5 crore DTH subscribers already in India. With respect to the satellite communications, with the advent of the ultra-high definition format and the 4K, the bandwidth and the capacity of the satellite which will be required in future is going to be increased. However, with the change in the viewership for personalized content, the role of broadcast satellite services is projected to be slightly diminished. However, the broadcast satellite services are not going to go away in the near future. With time, we also transited from single beam satellites to the multi-beam satellites. In case of a single beam satellite, the satellite covered the entire geographical area like India using a single beam, which was a wide beam. So all the users in this beam got the same data. The satellite payloads were also simple. Since the power on board the satellite was lower, as well as the EIRP and the G-bar T of the satellites were lower, the ground terminals were also of larger in size, as well as the data rates provided by the VSAT systems was only in the range of few kilobits per second to few megabits per second. With time, we transited into multi-beam technology, where the entire country was covered with multiple spot beams generated by the satellites. You can see here that the non-adjacent beams use the same frequency. Now, with time also, we migrated from lower frequency range C-band to higher frequency bands like Ku and Ka bands, where large bandwidth was available. Coupled with this, with the frequency reuse, large amount of bandwidth was available. The satellite had smaller beams, which means that they had higher ERP and higher G-bar T. So with time, the size of the Satcom VSAT terminals also reduced, and they became less than 1 meter. And the data rates also increased from few tens of megabits per second to even hundreds of megabits per second. And the VSAT systems provided broadband voice, video, and data communications. The fixed satellite service also evolved with time. They are being used for point-to-point communications and also for providing the last mile connectivity. We started first using C-band, later on Ku band, and then to Ka band. The power and the ERP of the satellites also increased with time, and the terminal size also reduced with time. Today, we are operating with ultra small aperture terminals with a terminal of less than 1 meters. About a decade ago, the high throughput satellites has a capacity of tens of gigabits per second. To today's generation of high throughput satellites have a throughput or a capacity of about hundreds of gigabits per second, and future, the days are not away when the geostationary satellite will provide a throughput of about terabits per second. Internationally, these kind of services are provided by satellite operators like Intelsat, Inmarsat, Viasat, SES World, Eutelsat, etc. The mobile satellite service is also one of the services provided by the satellite. Since the satellites have a very far reach and they can provide the coverage over very remote areas, the mobile satellite services or the satellite phones are also one of the important services using satellites. They are very useful for disaster management and search and rescue operations. S-band or L-band frequencies are used worldwide for these applications. In the olden days, the MSS terminals were of the briefcase size. From there, today, we have the satellite phones which are the same size of our mobile phones. In Mars, the Iridium was one of the first constellation to provide the mobile satellite service using 77 satellites, and it started the service way back in 2000, and it continues to provide the services today. ISRO also started providing the Satcom services like the broadcast satellite service, fixed satellite service, and the mobile satellite service. We also increased the capacity of the satellites over a period of time. Today, we have reached the stage where we are able to launch our own communications high throughput satellites which operate in Ku and Ka band. The satellite services scenario today is as shown here. The satellites are mainly used for long distance telephony. They are also used for cellular backhauling. They are also used for television services like television broadcasting, DTH, direct satellite news gathering services. They are also used for multimedia delivery like internet, IPTV, video and audio on demand service. Satellites are also used for mobile satellite service like satellite phones, satellite radio, television, and multimedia broadcast. VSAT services are the backbones of Satcom systems. For narrowband, they are used for stock breaking, ATM services for banking, internet, and e-governance services. For broadband, they are used for internet, cellular backhaul, etc. The satellites are also being used by the governments world over. They are being used for military applications, disaster warning, search and rescue operations, data collection platforms from remote areas, as well as for automatic identification system for tracking the ships, as well as for tracking the aircrafts all over the world. The satellites are also being used for societal applications like telemedicine, teleeducation, and village resource centers. The radio broadcasting is also an important service. Satellites are being used for radio networking, for terrestrial rebroadcasting, as well as for digital audio broadcasting. Coming to the requirements which are driving the Satcom applications, there are two types of applications, mainly the commercial applications and the government applications. Commercial applications are like smart city, bridging the digital divide, support to terrestrial mobile systems, and multimedia content distribution. When it comes to government application, it is the national security requirement, disaster management support, remote sensing data collection, and the satellite-based navigation. The requirements for the Satcom are like machine-to-machine communications, satellite-based Internet of Things, ultra-high definition television distribution, high data rate consumer broadband, satellite component of 5G, terrestrial backhaul, navigation services, in-flight connectivity for commercial aircrafts, maritime communications, and interactive TV. When it comes to government applications, there are satellite communications on the move, whether in land, air, or sea, or accurate satellite-based navigation services, high data rate transfer from LEO to the ground, space-based automatic identification system for maritime domain awareness, as well as the data relay services for the astronauts for the International Space Stations. The Satcom architecture, which is required to meet these demands, are like very high throughput or ultra high throughput satellites, multi-beam mobile satellites, high power broadcast satellites, flexible architectures, navigation constellations, and the LEO to MEO based satellite communications, multi-beam flexible satellites, data relay satellite systems, and hosted payloads for specific applications. Coming to the requirements driving the payload technologies, the three important requirements are flexibility, high throughput, and the modularity. For flexibility, the satellites have a long life of more than 15 years. They require a flexible coverage depending upon the demand of the areas. The satellites have to be moved over various orbital locations. The flexible gateway locations are also required. Moreover, progressively the services needs to be deployed. The flexible payloads which are required are for the flexible power allocations, active antenna systems, smart gateways, as well as onboard digital signal processing. High throughput satellites are required for very high data rate to small aperture terminals. Therefore, the satellites have to go into higher frequency bands like QV band, small beam size, and higher frequency reuse. Modularity is also required in order to reduce the production time as well as to manufacture the satellites using very low cost. For that purpose, generic payloads architectures with modular elements are needed. Coming to one of the important aspects, which is the talk of today, is the emergence of LEO-based satellite communications, which is considered to be a destructive technology which is emerging. Today we have seen that the satellites operators like SpaceX, OneWeb have already planned and launched some satellites in LEO constellations. Many other players like Telesat and Amazon are also venturing into the LEO-based constellations. These satellites are in low Earth orbit from 500 to about 1500 kilometers. The satellites are in multiple orbits, like in the polar orbit or the inclined orbits. The throughputs provided by one satellite is about tens of gigabits per second, and cumulatively the LEO constellation is grown to provide about tens of terabits per second of the data rates. There are many pros and cons of the LEO-based constellations. Coming to the advantages of the LEO constellations, they are in a low Earth orbit, so the RF power required by the satellite as well as the terminals is very small. The satellites have very low mission life, about 5 to 7 years, so they are built using cheaper payload components like commercial off-the-shelf COTS components. The launch costs are very low because of the reduced launch costs in the recent years with the launch of many dozens of satellites in one single go. One of the important features of the LEO is the latency of these satellites is very low because the signals have to travel very small distances. So these satellites are very lucrative for point-to-point interactive communications. And the advantage of this constellation is that they can provide constellation at very high speed all over the world. The challenges at the same time are also many. Mainly the regulatory issues are still being identified. There are a large number of satellites currently which is being planned, 1700 satellites from SpaceX already in space, and OneWeb has about 300 satellites in space. Debris mitigation is going to be a big challenge. Coexistence of this LEO constellation with the existing GEO using the same radio frequency from the radio interference point of view is also going to be challenging. Complex and expensive user equipments will also be required. These satellites are not particularly optimized for broadcast services. The constellation maintenance and replenishment every 5 years is going to be very costly. the network control and extensive ground infrastructure requirement, especially in the absence of inter-satellite links, is going to be very challenging. There are many Satcom experts who are also doubting the financial viability of these LEO constellations. Only time will tell about their success. In the meantime, the Satcom services from geo satellites is going to be continued, and it will provide very niche areas services to the whole world for the commercial as well as for the governmental applications. Thank you. With this, I complete my presentation.
Thank you, Dr. Parekh, for that enlightening presentation. I think the evolution was shown in such a clear and lucid manner that this is almost like, sitting in a classroom and getting a, a whole 360-degree view of all the things regarding the evolution with respect to the FSS, the BSS, and the MSS. It was brought out very nicely. So thank you for your presentation.
Thank you.
And when we come to NTN networks, one of the things that we see is that besides the satellites, we also have a lot of airborne communication. And our next presentation is, somewhere I would say centered close to high altitude platform systems. So I would like to welcome the next speaker, Dr. Pankaj Talela. Dr. Pankaj holds a PhD and MTech degree from in microwave engineering from IIT BHU Varanasi. He obtained his BTech from HBTI Kanpur, and he is currently director at CDOT. He has been with CDOT since 1996, and prior to that, he has worked in HCL Hewlett Packard as well. One of the significant achievements of research interests of Dr. Talela has been in the area of ICT in disaster management, IoT, telecom network planning, and design of geointelligence algorithms. Dr. Talela received the URSI Young Scientist Award in 2005, the Aegis Graham Bell Award for Innovative Managed Services in 2016, and the Elchina Award. He has published about more than 50 research papers in different national conferences and journals. And he has 5 granted patents from various countries. So I welcome Dr. Pankaj for presenting his talk. Welcome. Let me hand over to Dr. Pankaj now.
Good evening, everyone. Today's session of this THDSI Technical Deep Dive Conference 4th edition, the session on evolution of broadcast and non-terrestrial network. My topic is satellite and Wi-Fi PM1E. So what I am going to cover is what are the problems, difficulties to reduce the digital divide in India. So see, the requirement of seamless connections and extensive coverage, especially in rural and isolated area, have dramatically driven the development of non-terrestrial networks. The infrastructure requirements for local and regional connectivities are quite complex all around the world due to different geographically architecture. Mobile communication and its use in data communication is presently confined to urban areas where telco service providers earn better. In nutshell, if you see the average broadband connectivity in India, it is 51%, while in rural India, it is still limited to 29%. This data is from February 20 to March 21. The reason behind that is the rural population is not familiar the uses of computer gadgets and communication technology. Another reason is adequate infrastructure for broadband is not available. Third one is affordability. This population can't afford to have the individual broadband connection even if infrastructure reaches to them. and service provider cannot get adequate business model. Another thing is geographical area. The villages which is remotely located 5 to 10 kilometer apart with different terrains where population density is quite low and high technology has also not penetrated. For example, this optical fiber based technology or even 4G in the rural India wireless based is very less. The non-terrestrial network faces some unique challenges such as extremely long propagation delay due to long distance between satellite and user terminals. The combination of satellite communication as backhaul and Wi-Fi as access will be the most suitable solution for such regions. So how to address this thing? What should be the components and the solutions to address this digital divide? CDOT has designed several technologies for that. For example, CDOT satellite Wi-Fi CSAT-5 is an innovative integration of VSAT technology with our wireless broadband terminal supporting IEEE 8.2.BGN ACAX with 4x4 MIMO technology. The satellite connectivity is used as backhaul link for the complete area in this CSAT-5 terminal. C-dot BBWT systems such as solar Wi-Fi is used for hotspot and C-dot long-range Wi-Fi is used as point-to-point and point-to multi-point links to cover the complete village. The satellite and internet bandwidth can be provided by any existing satellite service provider and internet service providers. The network elements includes a C-dot autonomously designed CSAT-5 for rural deployment on rooftop of any Gram Panchayat building or location suitable for village. Wi-Fi access point to create Wi-Fi hotspot around the area for the delivery of service. Satellite remote station VSAT modem or smart LNB for backhaul connectivity through some satellite internet service provider. If we discuss for the use case, CSAT-5 is ideal for rural area connectivity, especially if you take for villages of very remote location and unconnected locations where the connectivity through optical fiber or radio link is not possible due to its difficult terrain. Now, second one is to establish connectivity to such location and for delivery of voice, data and internet connectivity, CDOT designed pole-mountable CSAT-5 to deliver services to far-flung and difficult terrain areas. This is suitable for northeastern states of India, Leh, Ladakh, Andaman and Nicobar Island, Lakshadweep Island areas of India, basically for difficult terrain. Now, what should be the delivery model? As I told that affordability is a challenge in rural India. So service delivery should be based on PM1E framework and delivery of internet service as per uses basis, that is Prime Minister Wireless Access Network Interface, this framework which has been approved by DOT. Service will be available through PM1E service provider like Messer CSC or any other PDOA. User need to install PM1E app for user registration and KYC. User can select the plan as per his or choice and enjoy the Wi-Fi service. Customized plan for users will be created as per requirement. That is duration based plan, volume based plan, speed based plan. This will be pay and use model after the proper KYC of the users. So here I am going to describe what this PM1E framework is. So as the Union Cabinet headed by Honorable Prime Minister Shri Narendra Modi ji approved the proposal of Department of Telecommunication to proliferate broadband through public Wi-Fi network under the framework of Prime Minister Wi-Fi Access Network Interface on 9th December 2020. It has primarily four components. That public data office, it will establish, maintain and operate only Wi-Fi WANI compliant Wi-Fi access point and deliver broadband services to subscriber. Then PDOA, which is aggregator of PDOs. It will be an aggregator of PDOs and perform the functions relating to authorization and accounting. App provider. It will develop an app to register users and discover WANI compliant Wi-Fi hotspots in the nearby area and display the same within the app For accessing the internet service, it also performs KYC of the individual users. Central registry, it will maintain in accordance the WANI architecture and specifications, the detail of app provider PDOS and PDOs to begin with central registry will be maintained by CDOT. So you see how this conventional ISP TSP network which is prevailing in country looks like, where this TSPs and ISPs core network is responsible complete AAA authorization and accounting, and then there like all the user credentials like password, username, and all subscribe plan and etc. is with TSP and ISP only. What are the data plans, payment gateways are using, KYC, they are responsible for that, access point database, logs for security agency, everything is residing with TSPs only. They are providing this Wi-Fi access point to the end user, and this connectivity is also through them, and different plans that way that individual subscriber get internet connections through Wi-Fi. This is conventional Wi-Fi network. So for example, at mall, railway station, airport, the complete network is managed by single entity, that is TSP ISP. From deploying access point to creating user authority, this application portal, maintaining core network, providing bandwidth, managing payment gateway, storing securities log, etc. Now, if I will see how this PM WANI network works. So here the entity, one is PDO, that is Public Data Office Network, where PDO take PM WANI compliant access point, and he takes the bandwidth from any of the TSPs or ISPs. Then we have this PDOA has to register itself to some PDOAs, that is the aggregator. So that aggregator is responsible for data plans, payment gateway, logs for security agency, and authorization and accounting. And it has WANI tokens also. And app provider, which individuals have to download that app, is having WANI tokens handler. It is responsible for KYC of through mobile OTP, and it is also having logs for security agencies, user profile, username, password, MAC ID, etc. It is being stored there, and all these three entities are integrated with PM WANI central registry, PDOA access point, PDOA database, app provider database. This is being integrated by CDOT PM WANI central registry. So this way this framework works. So how to this technical framework in brief way, if we want to describe that, but presently I have shown the pictorial view how they are being connected. So the complete ecosystem is unbundled. In TSP it was bundled into the one. Now it is unbundled as per the ease of users and PDOs individual. So this complexity has been divided. So Wi-Fi access point is deployed by PDOs. PDO takes internet bandwidth from any ISP TSPs. Wi-Fi authorization and accounting is managed by PDOA. App is created and operated by an app provider. So all these entities interop seamlessly and securely with each other with the help of central registry by complying to the framework. Multiple access points are managed by single PDOA. Access point has to be integrated with PDOA software. Any available access point cannot seamlessly work with the PDOA software unless it is WANI compliant. As per existing framework, if PDOAs has a roaming agreement among themselves, then the plan procured by subscriber of PDOA 1 can be used by network of PDOA 2. Further to continue, PM WANI complexity of creating and managing the Wi-Fi network is removed from a PDOA, local chai wala, kirana wala, bakery wala, etc., and moved to PDOA and app provider. From technical perspective, this unbundling is made possible by introducing WANI tokens in the architecture. Authentication credentials, username, password resides in app provider domain and authorization, and accounting functions reside in PDOA domain. When both app providers and PDOA come together, a user gets secured internet broadband through public Wi-Fi hotspot in a single click. WANI tokens enables user authentication, credential flow from app provider domain to PDOA domain. What are the silent features of PM1E? No registration, no license, and no fee for last mile Wi-Fi providers, that is for PDOs. No license fee, no fee, and a very simple registration for PDOA and app providers. Registration confirmation in 7 working days. Pan India license for operation. Unbundling of Wi-Fi network and services. Interoperable framework for anyone to become PDO, PDOA, and app provider. Proliferation of broadband in the country. Increase in income of small and micro entrepreneurs. Now, remunerative service in rural area using satellite Wi-Fi. Major services that could be delivered in villages are government to citizen services, that is PAN and Aadhaar card services, business to citizen services, mobile bill payment, railway booking, DTH recharge, etc., financial services, banking services, pension services, etc., e-bazaar services, tourism services, selling authentic rural and handicraft products, telemedicine services, telemedicine consult a doctor, etc., entertainment, infotainment services, and internet services. So to facilitate that, CDOT offering what CDOT has WANI certified PDOs, PDOAs, and app provider to enroll Wi-Fi services. So we have all these three parts: PDO, WANI compliant, PDOA, aggregator, and app also, white label app we are providing. So here are right side, you can see some of the pictures of our solutions, that is the PDO. And at the lower side, you can see this app glimpse and PDOA platform. So CDOT, an autonomous body and research and development wing of Department of Telecommunication, Government of India, has developed a range of indigenous Wi-Fi products and solution portfolio ranging from Wi-Fi access point, Wi-Fi 4, 5, and Wi-Fi 6, that is PM1E compliant. CDOT is also architecting and evolving the PM1E framework. CDOT offers its PM1E compliant access point, indoor and outdoor, PDOA aggregator, and app provider system and software as a platform to any of the PDOAs and app provider to enroll their service in the PM1E network. We have already started this cloud-based service model of PDOAs. So anyone can become PDOA, or anyone can buy our system of this access point, which is WANI compliant. So anyone can become PDOs. We are providing this app also, white label app, so that you can become app provider also. So come in complete PM1E framework, we have this solution ready, and these services we are providing. So that is all about which I need to say. Thank you very much.
Thank you, Dr. Pankaj. This was a very enlightening presentation, very innovative use of high altitude platform for solving some real problems in India. And I think I'm sure I encourage the audience to pose some questions. I think there was, any questions to the speakers. I would like people to post. We'll move quickly to the next speaker now, and. Yeah, I would like to introduce Sachin. Sachin Chibur is Senior Vice President looking after Spectrum and Technology Strategy at Ligado Networks, where he's responsible for technology development activities, ecosystem development, network planning, spectrum management, enablement, standardization activities, and technical regulatory programs. Sachin has over 25 years of experience in wireless network engineering, RAN technology, and RAN design, and he has worked on several wireless networks and has an extensive review of new network technologies, protocols, technological development, spectrum auction, valuation, Sachin did his bachelor's in electronics and communication from NIT Jalandhar and completed his MBA from Pamplin College of Business, Virginia. And currently, Sachin resides in San Jose, California. Over to Sachin for his talk on evolution of non-terrestrial networks.
I want to provide you some of my thoughts about challenges and opportunities that I believe the non-terrestrial networks present. And before I start, just a brief background about myself. I did my graduation from NIT Jalandhar and my MBA from Virginia Tech in US. I've been in the wireless industry for over 25 years now, and with my current company, Ligado Networks, for over 10 years. I'm based in California, US, and a brief background on Ligado is a mobile satellite MSS network operator serving customers in North America, and been business for over 20 years. And we provide highly critical communications to government, enterprise, and users. So moving over to my slides, before I start, basically a background on what NTN is. NTN is basically non-terrestrial networks. So basically networks which are not terrestrial. So these are not, so think of satellite, it could be a UAS, HAPS. Basically transmission happens from some equipment which is not tethered to the ground. So in case of Ligado networks, we operate a geostationary satellite. So basically satellite is at about 36,000 kilometers. And of course, there are other platforms, MEO in the middle Earth orbit, then LEO, LEO satellite, and they are in the lower, or there are a US platform which can operate at say 5 to 50 kilometer range. So this is, I think you might be familiar with this, but just wanted to level set on NTN networks. Then the next, basically there are two types of topologies that are being considered in 3GPP. One is called transparent payload and one is regenerative payload. So both of these have transmission at say satellite, but the difference being in regenerative is in addition to frequency conversion, frequency filtering application, they also do demodulation, decoding at the satellite. So as you can see, there's some when you need inter-satellite links, so in some of the architecture, there are inter-satellite links. So for those kind of topology, you need a regenerative payload. So in the case of Ligado networks, we are operating a transparent payload. So basically, it's a from hub equipment, there's a signal that is transmitted in Ku band, and then satellite translates into L band, lower frequency, say 1.5 gigahertz. Then the UE sent back the signal at 1.6 gigahertz. Then it's again frequency converted to Ku band to be received at hub equipment. So anyway, these are two topologies when we talk about basically NTN architectures. So moving on to my next slide is, so question of why is very important. Why NTN? What does the advantage does it provide? So this slide is basically summarizing some of the key advantages. So first is, should be pretty obvious. This is more service ubiquity. So think of in the case of Ligado networks, we are operating a geostationary satellite. So it can cover a very large area with a single satellite. So basically, when the terrestrial networks, basically service stops at say, I don't know, 5 to 7 to 8 kilometers when move out from a cell site. But in case of satellite, you can provide a coverage to rural areas, hilly area, doesn't matter. It's everywhere. Basically, services doesn't stop. It can cover a very large area. Then the service continuity. So here, think of, again, this is a kind of, you can continue your service when you move out of terrestrial network. So this can be a key differentiator in service. So if you have a NTN network and your terrestrial network, you can continue your service when you move out of the terrestrial network. So this is then the service reliability. This is, again, think of, you have a terrestrial network, you can have overlay it with a non-terrestrial networks. So you can increase your reliability. If something happens to your terrestrial network, you can still have a backup connectivity, and you can increase your reliability. Scalability. So as satellite covers a large area, so it's a very highly scalable network. So so you can enable service over a large area through this NTN platforms. And redundancy, this is again this is a somewhat related to service reliability, but this can also, if you need a highly reliable service, you can terrestrial NTN networks can serve as a redundant network, so it's providing you a backup, or they can serve as a, just by nature of NTN networks, they could be more reliable. They are not prone to, say, natural disaster as much as terrestrial networks are. So by itself, NTN can provide a highly reliable networks, but in conjunction with terrestrial network, they can also serve as a redundant network. So your overall reliability can go up. And rapid service deployability, again, in the case of terrestrial network, to build a network, you have to build a large number of base stations, whereas in case of NTN network, service can be deployed really rapidly. So think of a simple example will be US. So basically, US can go up to or HAPS platform can be deployed in a disaster area pretty rapidly. So there are use cases which can take advantage of these cases. And briefly talking about some of the specific use cases where they will be deployed, I think some of these are pretty obvious. Like I mentioned, EMBB, for example, you can have a very high throughput. You can have provide a backhaul through NTN networks, or these are pretty well known, but there are a little bit more interesting use cases which are in broadcast as well in IoT side of the. I will maybe touch a little bit more on these two slides. So there are some emerging opportunities for broadcast, which can be really a service differentiator with NTN networks. So think of, there are a lot of connected and autonomous vehicle which is a new trend, but to enable all of these are basically now computers on wheels. Basically, cars are has more electronics than even I guess robots of the past. So these are basically a robot. So but they do need a service update periodically. There are software firmware updates. And providing it over a terrestrial network, yes, it can be done, but this becomes a like say you need to send the same service update to, I don't know, say millions of vehicles, but a terrestrial network, you have to transmit a signal over each of the cell sites, so it's a very wastage of your capacity. Whereas think of your satellite networks, so you can have a beam covering, say, even actually it's possible to cover most of the, say, US with a single beam. So you can provide a highly efficient, basically a single stream can provide software update over a large area. So you can save on your throughput. It's a very efficient transmission of these kind of software firmware updates. And second, in the middle, I see say highly efficient delivery of GNSS correction data. I'm not sure how many of you are familiar with it, but the like GPS or GLONASS or most of the GNSS signals, their accuracy is within certain meters of distances, which are not good enough for say for example, in vehicle need to keep it in a lane, or even for agriculture applications, like for example, seed need to be planted at exact certain distances. So there are correction signals, which are again very small stream of data, but this again could be required for a large area. So these correction signals can enhance the correct, basically, position accuracy to in centimeter level. So this satellite provide a highly efficient mean of delivery of this kind of correction signals. And of course, mission critical devices where you need a highly redundant or highly reliable networks, satellite can play a huge role in these kind of opportunities. Another very interesting use cases which are opening up because of NTN networks is IoT use cases. So satellite have been in business, as I mentioned, even Ligado has been providing solutions for some of the fleet management, as well as other satellite companies have solutions in this arena. But challenge has been satellite terminal typically use a proprietary kind of or non-mainstream, non-terrestrial mainstream technologies. So typically they have been higher cost, but and terrestrial technologies can be, and NTN technologies can take leverage of the similar kind of ecosystem. So what it happens is, if taking advantage of the terrestrial ecosystem, cost will come down. So it opens up a whole new basically market of IoT use cases that can be enabled by NTN networks. So for example, think of logistic companies, let's say trucking company. Now, basically, for example, a trucking company could have a satellite NTN terminal which can act as a hub and can get the data from, say, various containers or various parcels which have through a Bluetooth connectivity or Wi-Fi. They could be localized connectivity, then it can be transmitted as a hub to satellite. All the IoT data can be transmitted with a low-cost terminal. Similarly, there are applications in agriculture, there's energy applications. But anyway, these were not possible because of the cost, form factor reasons. But with this emerging opportunity, this is opening up a huge IoT opportunities for NTN. And so this was the kind of opportunities why we are doing it. There are opportunities, but what are the challenges? So this is compared to terrestrial network, as you can imagine, geostationary satellite being at 36,000 kilometers, this is a huge propagation delay. So basically, delay can be for in case of geostationary can be close to like a 250 millisecond of delay. That's a large delay. So how do you handle that delay? So there are that's a new area compared to terrestrial network, where is delay is not even comparative. It's like not in, we're talking about single milliseconds range to 250 millisecond range. So these are the challenges that need to be handled, and these are geostationary challenge. This propagation delay is more applicable to geostationary satellites, but Doppler shift, this is, think of a LEO satellite. They may not have that much delay, but the LEO orbits move at a much faster compared to Earth. They are move at basically LEO Earth or satellite move at in a rotate around the satellite. So this rotation, this around the Earth movement, this cause a large Doppler shift. So how do you handle those Doppler shifts? And then the third challenge I've listed here is a moving fixed beam. Sometimes, because satellites, in case of say LEO satellite is moving, so whether beams are fixed respective to the Earth, or the beam also move with the satellite, how do you have that handoff? So these are challenges that need to be handled. So differential delay, this is another very interesting area of that is being handled. How that challenge is being handled in as part of this NTN development is geostationary satellite can cover a large area, but then within two users within the same beam, they can have a differential delay to the satellite. Then that delay, the difference in delay can be large. So there are ways to handle that. There are technologies that need to be developed, or there are ways to handle that differential delay, but this is a challenge in itself. The fading environment. So in the terrestrial technology, most of the propagation channels are fadings are more Rayleigh type of fading in non-line of sight channels, whereas in case of satellite, think of most of the actually signal is more line of sight. It's more of a Gaussian type of fading. So different channels, propagation channels need to be considered. Then the handover, again, this is again, if let's say beam is moving, you can have a very large signaling overhead. Or how do you manage a tracking area? There could be a beams which can cover a two countries. How you can have a multiple tracking areas within a beam, or so these are all challenges that need to be handled. Power limit, again, this is related to the large distance. So large distance means, and link budget wise, power becomes a power limited link budget. So and duplex schemes in the terrestrial network, most of the band higher than, I guess, 2.5 gigahertz upward are really the TDD bands. But whereas in satellite, most of the, even at the higher frequencies, channels are not TDD, they are mostly FDD bands. So basically uplink and downlink happens at different frequencies. So that reciprocity that you could have taken advantage in the terrestrial network, that advantage may be gone in the NTN networks for the higher channels. So again, just wanted to provide you some background on what are the challenges that are being handled in 3GPP. So all the challenges, yeah, so there are companies that are working, they collaborating to solve it. Of course, Ligado is a part of 3GPP, and we have been pushing, we are very proponent of this NTN technologies. So in 3GPP, in release 15, there was the first time they did NR NTN study. That was part of release 15, and it was completed. And the release 16, there was another NTN NR study item. Then in release 16, it introduced the NTN as a formal feature for the first time. That work is ongoing, and it's on target to be completed as part of release 17 towards middle of next year. NTN IoT study item. So this was so Ligado was as a company, we kind of working towards standardization of this work item also. So study item has already been completed as of June of this year. And after completion of study item, this was made a work item. So this is on target to be completed as part of release 17 next year. And that work will not stop with release 17. There will be additional enhancement required for both NR as well as IoT. For example, there's a how to HARK enable or disable. Anyway, there are a lot of newer feature that will need to be need ongoing development. So those will be part of release 18, and actually that definition is still not complete. And expectation is release 18 definition will be completed by end of this year. That's the plan. And actual work can start in sometime with the release 18 around July timeframe. So that is what is happening in 3GPP on the NTN front. And then moving on to frequency bands. As you know, in the terrestrial network, there was this FR1, FR2 bands. FR1 was less than 6 gigahertz, then FR2 was greater than 6 gigahertz, and the channel numbering was for FR1 was started from channel 1 onwards, and FR2 was 257 onwards. And there was a designation of N for NR channels. So that's what has been for terrestrial channels. So recently in the WG4 meeting in August, decision was made to numbers this NTN channels going backwards from 256. So channels will be 256, 255, 254 in that arrangement. And there will be some prefix SORAN that has not been decided yet. And as of now, there are two frequencies band that frequencies have been decided as of this August meeting. So Ligado band, we operate in L band, that would be channel 255. So let me actually, I'm running out of time, so let me move. So let me give you my information. You can reach me at sachin@ligado.com. It was pleased to meet you. Maybe I'll I'll be able to answer some of the questions next session. Thank you.
Thank you, Sachin. It was a pleasure hearing from you. It was a very engaging session. And I think the kind of challenges that you depicted, it looks like it needs a much bigger session. We are, of course, definitely don't have time. So I'll move over to the section on questions. I see some questions in Q&A. Okay, so I'll ask the question. I think some of them are getting answered by the speakers. Does India need exclusively dedicated high throughput satellite for BSS?
Yeah, I'm K.S. Parikh. Answering to that question, typically the high throughput satellites have large number of beams over a given region. So ideally, they are not suited for broadcast applications. But yes, if we want to use the high throughput satellites for only region-specific content, then that particular satellite can provide very high ERP, so and very large bandwidth is available. So very large amount of data rates can be available. So these high throughput satellites can be used for a hybrid kind of services for both broadband as well as for the broadcast services. So yes, they can be used for broadcast. But we don't need a exclusive broadcast high throughput satellite. Any high throughput satellite, part of the beam, wholly or partially, can also be used for broadcast purpose.
Thank you, sir. Thanks for your reply. The next question is, Sachin, for you. Can you explain further the duplex challenge mentioned as the last item on slide number 8?
Yeah. Hello. Thanks all. Yeah. So in India, challenge is basically most of the satellite that operate in the terrestrial side, most of the frequency above 3 gigahertz, they are designated a TDD channel. So how it works in TDD is you have this reciprocity. So basically you can uplink can be estimated based on the downlink signal you are getting from satellite. So you know what is the fading, whatever is the downlink fading, you are expecting the same fading on the uplink. But in case of satellite, these higher frequencies are allocated as FDD band. So the reciprocity does not exist. Basically, for example, say downlink is on say 24 gigahertz, uplink is on 28 gigahertz. So whatever fading you are seeing on 24 gigahertz, that may not be same at 28 gigahertz. So how the standard CPP standards are defined for TDD may not be applicable for those frequencies because they are being used as FDD. So there are those challenges. Of course, that work is ongoing to how to address that, but that's one of the challenge. Is that clear or?
Yeah, thank you, Sachin. I think thanks for your answer. I think the next question is: any regenerative payload will be needed in future for India bases or other services? I think Dr. Parikh, you couldn't take that.
Yeah, coming to the question of the use of regenerative transponders for the future satellites. I think when we are going into the era of high throughput satellites, the bandwidth is very large, typically in the range of many gigahertz of bandwidth. Now, once we use the regenerative kind of transponders, definitely there is an advantage in doing so because we can use different the adaptive coding and modulation for uplink and the downlink. So the uplink and the downlink bandwidth can be individually optimized depending upon the link margins available either for the uplink or the downlink. but that requires for the demodulation of the signal on board as well as the remodulation on board. That requires a very large amount of digital signal processing, and it also requires also a large amount of the power for processing of the signals. So it looks like that the next generation of the high throughput satellites will not be regenerative, but they will still be the conventional transparent processors. But recently, I also read that for the LEO constellations that are being used by various service providers, they are now going ahead with the regenerative transponders, so that the ACM can be used separately for the uplink and the downlink. So the uplink bandwidth can be very efficiently utilized. Yes, so there are advantages in going for regenerative transponders. But considering the geo satellites, which have a typically very large lives, I mean, of about 15 to 20 years, and since the technology is changing very rapidly, I don't think that the regenerative transponders will still be considered for high throughput satellite, especially for the geo orbits.
Thank you, Dr. Parekh. The insight is really, really useful. I think this is great conversation. I'll take one last question. This is for Dr. Pankaj. Question is, how much is the bandwidth per user provided by CSAT-5? Actually, there are three questions. Could you please throw light on long distance Wi-Fi range, bandwidth, any changes in protocol to take care of propagation delays? Sir, it's on the Q&A window if you could address that question. Sir, you are on mute, looks like. Can't hear you.
Maybe, sir, please remove earphones.
So we are not able to hear you. No, sir, you're not audible.
Sir, switch to lower bandwidth. There seems to be a network issue.
Hi, sir. Hope we are audible to you. Can you just refresh your page? You will be redirected again in the URL bar. Just refresh your page once, sir.
Am I audible now?
Yes, right.
Yes, sir. Loud and clear. Yeah.
Yeah. So the first question is regarding this satellite bandwidth CSAT-5, this system. So it depends, the bandwidth depends on the type of backhaul which we are receiving from satellite. If we are taking, say, suppose 2 MB link, then it depends on that. If it is higher, then it depends on this one only. In hotspot, it depends how many subscribers are present. So since satellite bandwidth is costly, so it depends on the backhaul which you are taking. But suppose if you are taking 2 Mbps, then nearby subscriber and subscriber density is less. So accordingly, they will get it. Another question which you have asked about this, how much range which you are getting point to point is typically we have tested 10 kilometers, and we are getting in line of sight in Wi-Fi 5, we are getting around 700 Mbps up to bandwidth. And in case of Wi-Fi 6, we are getting in this for 7 to 8 kilometers, we are getting in around 800 Mbps, up to 1 Gbps we are getting. This we have tested. In Maharashtra, our 10 links are working point to point in Akola district, and other places also we have tested point to point link. Up to 10 kilometer, we are getting good this throughput.
Okay, thank you, sir. I think that was, I think the CSAT-5 is definitely a great innovation, and I think we are really proud of CDOT for this innovation. So actually, I'm running out of time. I was supposed to finish my concluding remarks. So thank you all the speakers, and for this, for this very engaging discussion. I think the deliberations were really top notch. I felt that, I think I would like to thank the organizers of TSDSI. This was the first time where we introduced these sessions of dedicated sessions for broadcast and non-terrestrial networks, and looking at the number of people who are still with us at the end, I feel that we will definitely, this will grow more and more. I feel even the study groups inside TSDSI, I mean, some of the work related to NTN and broadcast will also get reflected in terms of the study items which are taken in both these study groups. So I think with that I will conclude, and I will hand over to um, Bindu or for the next session. Thank you to all the speakers, and thank you
Thank
to
you.
the audience for
Thank
staying
you.
with us.
Thank you, sir.
Thank you. Thank you.
Thank you.
Thank you.